Good morning or afternoon, depends on where you are, and Happy New Year. My name is Andy Deal. I'm your host today, and welcome to our first webcast of 2017. Today, we're going to talk about modernizing your simulation process, and our guest presenter, actually our presenters, are Jeff Freeman and Daniel Rubio, two of Ceratec's best. I have a quick reminder for everyone before I pass the presentation over to Jeff and Daniel. During the presentation, if you have any questions at all, go ahead and type it in your chat panel and we will address them when we get to the Q&A portion. Also, after you log off the webinar today, there's a short survey. There's only, I think, 5 questions that pops up. If you can just do me a favor and take about a minute or two to fill that out, that will help us out a lot. With that, I will pass the presentation over to Jeff and Daniel. Over to you, Jeff.
Thanks, Andy. My name is Jeff Freeman, and I'm a solutions consultant here at Ceratec. I'm based in Atlanta and cover several states in the Southeast for Ceratec. We're the largest Siemens reseller in the country, and I'm responsible for sales of software, services, and training. And also on the call is Dan Rubio. Dan, if you wouldn't mind introducing yourself as well.
Sure, thanks, Jeff. So like you said, my name is Daniel Rubio. I'm an application engineer with Ceratec. Been supporting CAD and CAE with Ceratec for over 5 years now, and I'm based out of South Florida.
Great, thanks, Dan. So this webinar will last approximately 45 minutes, give or take a couple, and where you'll get to see our solution and its benefits. In case you have to drop off early or you'd like to share what you saw with your colleagues, a recording will be made available. We'll take questions at the end, and we have a lot to cover, so let's get started. So in this webinar, we'll be covering 3 main chapters, and we'll address many of the issues that can be found in the simulation process and show how they can be overcome. The areas we'll be looking at will be the creation of an FE model, going from reading it in CAD data to idealization, and model setup. Then we'll look at post-processing of results, and then how that can be handled efficiently. Finally, we'll look at how you can streamline your workflows, in particular the power of the Application Programming Interface, or API, and how you can efficiently work with legacy models. So FEMAP is the graphics program that provides pre- and post-processing functionality to build the simulation model and prepare it for analysis by the solver, and then review results afterward. FEMAP opens open simulation by both being CAD independent, where CAD data can be accessed from just about any source, and solver neutral, and that FEMAP can create simulation models for all the major commercial solvers with a high level of integration with the Nastran solvers. The modeling and visualization capabilities are all accessible within an easy-to-use and intuitive user interface, which brings many benefits, including increased productivity, a reduced learning curve, and training overhead. So who uses FEMAP? So we've got a few slides that just shows a sampling of some of the larger customers across the planet that all use FEMAP. So we'll go through these pretty quickly. I'm sure you could recognize quite a few of these. So in this first chapter, we'll cover the areas in pre-processing where FEMAP can help you create an accurate FE model as efficiently as possible while overcoming the traditional obstacles that analysts face every day with the use of an existing CAD data, idealizing that CAD geometry, and then the process of meshing that geometry to create an FEA model. So the flexibility of data flow is key to a standalone CAD independent program like FEMAP. FEMAP can leverage and import the CAD model for most CAD systems and then use it as a starting point to create the simulation model. The FEMAP modeling engine is based upon the Parasolid modeling kernel, which is the same as that used by SolidWorks and Solid Edge and others. So FEMAP and Solid Edge are fully associative, which allows the direct transfer of parts and assemblies. Once the CAD model has been successfully imported into the simulation environment, there are various challenges that have to be overcome. In general, the CAD model contains more information than is required to create a simulation model with details like fillets, chamfers, and holes that may just be too small to be of any significance. If left in the model, they will lead to the creation of small elements that try to capture the small detail, giving rise to overly large FEA models. Besides small detail, the CAD model may also contain problematic geometry that can impede the creation of a finite element model. Items such as sliver surfaces, short curves, etc. will misguide the mesher, and if left unheeded, can lead to the creation of badly shaped elements. So how can FEMAP help? Well, FEMAP has tools that will automatically or manually defeature a model without oversimplifying the model data or losing any vital modeling detail. So locating and removing troublesome geometry such as slivers, gaps, short edges is one of the main challenges that has to be overcome in the creation of a finite element model, as they lead to badly shaped elements. Even finding where these problematic entities reside can be a major task. This is where FEMAP's locator on the meshing toolbox comes into play. It's a dialog that you can use to control the search parameters and then locate all of the troublesome curves and surfaces quickly and easily. Having located the problematic geometric entities, there are a number of tools available in FEMAP to make corrections and allow an accurate, well-shaped mesh to be created, such as combining curves and surfaces to merge adjoining surfaces and producing a smoother, more regular geometry model that's ready for meshing. Some other aspects of geometry handling include the ability to remove unnecessary features like small holes, fillets, and chamfers from the geometry model, again, to create a better mesh. Besides the manual tools available for geometry cleanup, FEMAP also provides automatic capabilities for geometry preparation, which makes the task of meshing much easier and faster. FEMAP performs some proximity checking, which also allows unnecessary detail and small features in the geometry to be identified and removed. The methods of removal are similar to the manual tools mentioned previously and include combining surfaces and curves, small features of suppression, and surface splitting at strategic locations. The extent of geometry changes is controlled overall by user-defined tolerances. Here we'll cover the typical challenges that arise when trying to create a more efficient and accurate FE model. More advanced analysis like dynamic response and nonlinear are more numerically intensive and can also require an approach requiring multiple solves. So there are certain approaches in finite element modeling that adopt different model topologies to improve the efficiency of the model by reducing the model size without compromising accuracy. Solid element meshes cannot realistically be used to represent certain modeling topologies such as thin-walled or frame-type structures. The resulting models would be unmanageable. This requires a departure from 3D to 2D and 1D or finite element types through model idealization.
Thanks, Jeff. So let's talk about some of those tools we can use. First off, mid-plane extraction is a very powerful tool designed to deal with these thin-walled structures that Jeff just mentioned. These geometries are difficult to model accurately using solid elements. You're going to be creating huge, unmanageable simulation models, so those really lend themselves to being modeled using 2D shell elements or plate elements. So you create a much smaller but still accurate model of the structure. Mid-surfacing tools in FEMAP offer both automatic and interactive manual options, and you can handle varying thickness solids as well. There's many options to hide the exterior surfaces, which greatly enhances the visualization of your model and greatly facilitates working with surfaces that are interior to a solid. FEMAP also automatically applies offsets and thicknesses from the original solid geometry to the elements meshed on those surfaces, so that ensures that your FE model matches the original geometry. A big part of modernizing the workflows associated with geometry updates and manipulation is really evident in FEMAP today, with the ability to work directly and interactively with the geometry and that you see on the screen. You can pick points to be moved. You can click on 2 points and the surfaces connected with those points will join together automatically for you. When surfaces are joined in this way, they're automatically connected together to form a single closed body, so you don't have any free edges. Using these techniques, it's possible to move entire entities. You can move a particular aspect of an entity to extend the width of a slot, for example, or remove it completely by deleting just a single edge. Again, this is all direct and interactive, so geometry editing is fast. Another important modeling capability for consideration when you're talking about geometry idealization is beam modeling. FEMAP offers a method of automatically determining the physical properties of any cross-section that you define. And it also offers a library of commonly used cross-section shapes. You also have full beam visualization that's available to you, so you can view beam element results as if they were solids, so it's very easy to check the orientation and offsets for beams. And once you solve the analysis and are looking at results, you can view the beam shear forces and bending moment diagrams as well, and also output the contour plots. One customer of ours, Spaceworks, took full advantage of all of these advanced modeling functionality that FEMAP offers when they designed the next generation plug-and-play satellite structures. A series of elegant but very complex FE models were created using FEMAP to quickly gain insight into the structural performance of the spacecraft structures. If a standard design approach had been used to simply mesh the geometry with tetrahedral solid elements, the resulting model would have contained tens of millions of nodes and elements and would have been way too large to solve. But using a hybrid hexahedral and plate element approach, they were able to get a much more manageable model with only 800,000 nodes, and that proved to have a very good correlation with the experimental results.
So the meshing determines, thanks Dan, I appreciate that. Meshing determines the degree of model discreditation and also has a direct impact on final results accuracy as well as the efficiency of the solution. In the creation of a finite element mesh, it's important to create a mesh with well-shaped elements. The more distorted the element, the more inaccurate the results that element will display. Badly shaped elements can even stop the solver from completing the analysis. Locating bad elements in a model can be difficult and fixing them time-consuming. Model checkout is therefore important, and a lot of time can be saved if errors in the mesh are found before the analysis is submitted in the modeler, where they can be dealt with efficiently. FEMAP helps with these issues with a powerful meshing capability through the interactive meshing toolbox. Other issues that can be covered in this chapter include the modeling of complex loading conditions and modeling composite materials. FEMAP offers powerful capabilities in these areas.
That really is awesome, Jeff. So here's that meshing toolbox that Jeff just mentioned. It is fully interactive and lets you modify geometry either prior to meshing, or also you can use it to update an existing mesh. So you have different tools such as geometry splitters, which can be used to split large surfaces into smaller ones that can be mapped mesh to get more regular quadrilateral elements. You also have offset curves, which lets you create map meshable regions around complex geometry with various curves like you see on the bottom left here. You can also add washers and pads, which can be used to add offset curves or squares to create map meshable regions around holes, which are typical stress razors. So you would usually want to have a very good refined regular mesh around those holes for accuracy.
Thanks, Dan. So here you can see you have full control of meshing parameters on the underlying geometry with the meshing toolbox, as well as setting the number of elements on the edges or surfaces of curves. You also have further options to select mapped meshing, which ensures an even distribution of well-shaped elements over surfaces. And for very detailed mesh adjustments, you can manually move individual nodes around on the underlying geometry And FEMAP ensures that they adhere to the underlying surface or curve, which can be useful to improve the element shape so that it can pass the selected element quality criterion. Element distortions and other element quality checks are included in FEMAP's meshing toolbox and can be shown interactively during the meshing process, which is a good quality mesh in areas of high stress gradients and is important for accuracy. Some other checks available on FEMAP allow you to verify that there are no discontinuities in the model by viewing free edges and faces, which is something that cannot be checked by just looking at the model. Also check coincident elements and nodes, which can also be indicators of discontinuities, load checking by summing forces, and mass property checking. So a powerful method of simulating complex loading within FEMAP's pre-processing functionality are the data surfaces, which are useful to define more complex loading conditions. Data surfaces come in various topologies from 1 to 3 dimensionals, as well as some special cases. Another example shows how a temperature distribution can be oriented and applied to a component for further analysis. FEMAP also offers the ability to automatically determine contact between assembly components, and beyond that, to easily define the nature of the contact, whether it be linear or nonlinear, with or without friction, or glued. Besides contact and gluing, FEMAP offers other methods of connecting components, including weld, spot weld, fastener elements, and bolted connections, which can be preloaded. So no matter how the assembly connects together, there's a suitable option available within FEMAP to ensure correct interaction and hence correct load transfer between the assembly components. I'm sure many of you are very familiar with the ever-increasing use of composite materials in manufacturing, which seems to be quite the growing trend these days. FEMAP has various capabilities that can help you quickly view and understand an existing model or create a new layup from scratch. A big challenge with modeling composite materials is visualizing the model and layups. FEMAP's grouping functionality can help here, as you can define groups by layup, which makes visualization very easy. With the idealization of composite structures, ply discontinuities due to drop-off create situations in the finite element model where adjacent elements contain differing numbers of plies. Results interpretation of composites can therefore be a laborious task requiring manual identification of corresponding ply results from element to element across the structure. The FEMAP global ply capability addresses this problem by allowing you to identify global plies and then use them to visualize results on continuous plies across the structure.
Thanks, Jeff. That really is some powerful stuff there. So let's see a demonstration now of some of these geometry idealization and meshing tools that we've been talking about, and we'll also set up some boundary conditions and analysis parameters. And we'll also see some of FEMAP's visualization tools along the way here. So you can see a solid bracket, but you can see we have varying thicknesses around the bottom base of this part. So we can throw a temp mesh on here, and of course we get a very good quality mesh. You can see the collapse. The worst aspect ratio is 7, which is fine. But we have about 80,000 elements. So let's see what else we can do. We can actually use an automatic mid-surface command to represent the geometry using a 2D plate or shell type element. And here, just showing in a transparent view, we can see the rest of the solid that we use to create the mid-surface. But we have all of these lines that separate those different thickness areas, as you recall from the original geometry. So we can use a meshing toolbox to basically imprint all of those edges to separate all those faces, so we can get those varying thicknesses. So once we have imprinted all of those separate areas, we can turn that solid geometry back off, and then of course use the meshing toolbox and many tools to get a very nice mesh like you see here. But of course, we still don't have those different thicknesses represented. So we can add a constraint to the nodes on the bottom, for example, and then very quickly show a visualization of the thickness of that plate. Here we can see it is a constant thickness that we define, but with a quick update of the properties, you can see we can immediately have FEMAP automatically update all those different thickness areas. And that is automatically retrieved from the original geometry. Once you have all that done, you can run the Nastran solution and come back and post-process your results directly right in FEMAP. This is all automated. For example, a modal analysis, you can quickly see all of the frequencies and, of course, animate them and view the exaggerated, of course, in a modal deformed plot, where we can see what the structure is doing in this analysis.
So in the second chapter, we'll cover the areas in post-processing where FEMAP can help you efficiently view and comprehend the results, giving you a quicker understanding of model behavior. We'll cover some of the advanced post-processing capabilities that FEMAP offers, and then look at free body functionality that can be used to gain an insight into how loads are passing through the model. As models continue to get bigger, the amount of results data produced by the solver also increases. When you also consider performing a more advanced type of analysis, such as a dynamic response or nonlinear analysis, then the data created increases even more, as these types of analysis produce incremental output data in steps of time, frequency, or loading. This then gives rise to the various challenges such as long import times to read in the results data, increased memory usage in processing the results data, and also managing the consequentially large database files. FEMAP can help with these issues with the ability to attach results files to the database instead of reading the results data in. In a benchmark test, to test their external results capability, you can see that the data access times were much faster when attaching rather than importing the data. Also, a lot less computer memory was used for results post-processing. Another issue is the ability to view the results efficiently. As we've seen, the amount of results data created by the solver can be potentially huge, which makes the task of going through and reviewing the data much more onerous. For the sake of speed, this requires a set of tools that will allow you to review the critical results data efficiently. These tools should also help you comprehend the behavior of the design and allow you to communicate the findings effectively.
So output sets can be organized into analysis studies to help order the output data into more understandable groups. These studies can be created automatically or also manually when you are attaching the results data, like Jeff just talked about. Organizing your output data in this way makes it much easier to find, also even to delete, and do different operations on a collection of output sets from all your different analysis runs. So for example, you can group output sets from a statics run, a modal analysis, or even time steps from a transient analysis, all into separate analysis studies and operate on them separately. You can even animate studies to create a multi-set animation using all of the output sets in a study. There's also a tool that lets you create an envelope, basically, which will create a complete output set using the selected type. For example, a max stress, minimum, or even a maximum absolute value for all of the output sets that are in that study. There's a result set processing data surface available that we briefly talked about before. So different factors can be applied to each output set using a spreadsheet-like form. And then post-analysis, FEMAP offers some very powerful functionality to help you review all the results and understand the behavior of the model for applied loads and boundary conditions that you have. Typically, a lot of results data can be generated by the analysis, so the ability to investigate all of this data efficiently and present it concisely is one of FEMAP's strengths. You can animate display plots, for example, view results inside a solid model with the dynamic cutting plane, as well as the dynamic ISO surface tool. And FEMAP offers full control over your desired output requests, and you have many options, of course. And also in terms of exporting results from FEMAP, all the standard forms of image and animation output are supported, including JT files, which allow interactive review of the model with the results. And for easy access to all these viewing options, the post-processing toolbox is available, similar to the meshing toolbox we saw before. This consolidates the most popular viewing options into a single pane or a window. This allows you to set up and change the options interactively, so it reduces the learning curve and also the training time to become proficient very quickly in using all of these post-processing capabilities. FEMAP can also show detailed beam cross-section contour plots of the stress distributions and also the shear flows to reveal the full beam behavior in an analysis. You have full control of the forces used to calculate the stress distributions and also different stress types, such as von Mises, can be calculated. And you also have many other forms of beam results, such as visualizing the bending moment and shear force diagrams for these beam type structures. So let's see a demonstration of some of these beam post-processing tools. So we'll see how to apply some load factors and post-process those additional virtual output data sets as well, and show some of the detailed beam results capabilities. Here we can see a structure which was originally a solid, but we created some mid-surfaces as well as some beam structures to simplify the model. Here we can view an animated plot. Of course, again, this is exaggerated. But we have many tools so we can see the different results. In this case, we have 3 load cases for the X, Y, and Z. So you can see the structure deforming in all 3 of those directions. So we know that the analysis was correct. Here, let's say we have an Excel sheet with a simple load combination table. We can actually copy and paste that into our load combination. And very quickly, you can see we can create many additional load sets to save you tons of time. Once you have those set up, we can very quickly the beam results isolated, for example, as you see here. We can very quickly pick up on all these virtual output sets we just created using the factors and combinations here. Then we choose the beam output results we want, and we can view those results in the data table, which can of course be then sent to Excel or Word or any other type of document you want. And also on the FEMAP screen itself. We can use the beam cross-section controls here to visually see the different beam results. And you can see you have many different factors that are taken into account: the axial force, shear forces, moments, torques, and so on. So depending on what you want to include, of course, these plots will appear differently. Notice a combined shear stress in this case, or you can also view a vector plot. This will definitely show you a great representation of the actual shear flow going through the model. Or instead, you can of course view the specific Y shear stresses, Z, for the von Mises stress, or the entire structure as well. And as I mentioned before, choosing the different output information will of course change those results. So you can choose to include the shear force in the Y, the moment in the Z, and so on.
Thanks, Dan. So as mentioned before, FEMAP offers full control over desired output requests of the analysis itself and results selection for review. XY plots are available with a recently expanded charting capability, and for visualization of shell models, contour results can be plotted on shell elements as if they were 3D elements, showing plate thicknesses with a linear stress interpolation throughout the thickness. In the FEMAP user interface, there's a pane that's dedicated to the charting functionality that can display XY plotting data in a modern format that can be easily inserted into a report. You can create data for charting from various sources such as results data or function data, and the charting data is automatically updated when the source data changes. And of course, you'll have full control over chart styles, including line styles, colors, markers, grid lines, and fonts. Another method of manipulating output data in FEMAP is the data table. You can send either modeling or results data to it. The data table then allows you to sort, filter, and evaluate data that it contains. You can use it to rank results or compare data from different output sets or models. You can also copy the data to the clipboard and then transfer it to the third-party programs like Microsoft Word or Excel. Another issue is the ability to clearly evaluate running loads through the structure. Model and results comprehension can be very time-consuming. So to help do this, FEMAP includes the free body capability, which accesses and visualizes the grid point force balance output data. You can generate free body diagrams, interface loads between components within the model, and calculate and view section cuts. Grid point force data recovery that is calculated by the solver provides some very useful output that helps to determine load paths throughout the structure. FEMAP then provides a couple of capabilities that work with this data to provide free body diagrams for parts and components, and for more detailed scrutiny of interface loads between components in the model. Global local modeling is a general topic where results from a coarse global system model are applied as boundary conditions to a more refined model of a component or subsection of the global model. FEMAP has implemented tools to help make this process easier for the user. The new tool allows the user to select source nodes in a global model free body and target nodes in a local refined model. The tool then creates RBE3 connections in the local model to apply the free body loads and automatically creates local model load cases from the selected global cases. The RBE3 connections can be edited interactively using the new graphic rigid element editing tool. Multiple load cases are supported, and all selected cases in the coarse source model are then copied into the detailed model. One of our great customers, Lockheed Martin Space Systems, uses FEMAP with NX Nastran as a solver for the design of the multi-purpose crew vehicle and faced challenges that included analysis that required over 900 load cases and large models up to 1 million elements and a high volume of results data to sort through. Keys to their success included more efficient workflows due to the tight integration between the solver and pre- and post-processor ability to import ProECAD data. As a result, the company successfully completed complicated case studies in a short period of time. They saw improved accuracy due to FEMAP's geometry manipulation and visualization tools, the ability to sort through many load cases utilizing the data ranking and free body functions, and then FEMAP's API, which allowed automation of routine tasks, saving time and increasing accuracy. So in the last chapter, we'll look at a couple of aspects of how you can streamline your simulation workflows. We'll review some of the capabilities FEMAP can offer to help you work with legacy models. Also, when you have a repetitive task to perform, we'll demonstrate how such tasks can be automated through the use of FEMAP's Application Programming Interface, or API. A number of issues arise with dealing with legacy models. You may only have the bulk data and no geometry, so how can you then make changes to the model easily? Alternatively, you may have both geometry and the bulk data, but from separate sources. So how can you reassociate the two to create a single model? Also, you may be faced with the task of having to merge different models together, which are likely to have interfering numbering systems, which can be a tedious, time-consuming task. FEMAP offers a number of tools that can help with each of the above situations, We'll take a look at them in the next few slides. FE models can be updated or remeshed more easily. You can work on individual patches of the original mesh and turn them into geometry, which is automatically associated to that mesh. With the new geometry in place, it can be modified using the geometry tools and then remeshed. Further mesh changes can be made using the meshing toolbox, or you can simply delete the mesh once you have the geometry and add cutouts and other modifications and then remesh. So let's look at an example of how you can create geometry from a mesh for even challenging shapes by adopting a simple procedure. In the model shown here, the first task is to identify simpler geometric parts of the FEA model, rectangular areas isolating highly curved parts of the model, and then create geometric surfaces from these patches of elements. Once all of the geometry surfaces have been created, they can then be stitched together, producing one single solid. So at this point, you have a geometry model that is representative and has the same topology as the initial FE model, and you can now make any changes that are required to this geometry. Then once all the required changes are complete, simply remesh the updated geometry to create the new mesh. You may be faced with a situation where you have moved a finite element model and a geometry model over from another system, but the method of transfer requires separate paths, leaving you with two separate models. FEMAP easily can reassociate the two together so that they both exist in a single database. Naturally, the models must share the same topology, and you can specify search tolerance to control this. There's various other controls that can help to guide the process, and FEMAP can provide a detailed summary at the end of the operation. This slide begins the discussion of the file merge command, commonly referred to as the model merge. The model on the left represents a portion of a fuselage, while the model on the right represents a section of subfloor structure. Notice how the two models are not aligned with regards to the global rectangular coordinate system, but that's okay because they can be addressed when using FEMAP's model merge capabilities.
Thanks, Jeff. So here, sorry, skip the slide there. So listed here in the model merge command, you can see all the different entity types which can be merged from one model to another. And also notice the entity selection, renumbering, and model orientation and transformation capabilities of this model merge tool. You can select any other currently open model to merge entities into the currently active to model. The entities listed in the merge extract section will be changed automatically if you change the from model. You have many options to choose what to bring in, as well as methods for renumbering all the entities as well. One other major thing to mention here is the ability to transform the entities in the from model using a coordinate system and align them to a coordinate system in the to model. So you can see an animation of the various instances being placed of the subfloor into the larger fuselage model. So when you're dealing with results data, it's often necessary to create additional load sets that are combinations of the load sets calculated by the solver. FEMAP can do this easily using the load set combination data surface, where you define the load set combinations in a spreadsheet type format like we saw before. Combination factors can be entered manually or pasted from an Excel spreadsheet. The summation of the constituent load sets is completed on the fly, and the new combination load sets appear in the load section of the model info tree. As for the actual solving, setting up solver options for each model takes time, and engineers unfamiliar with a particular type of analysis may not know what is required. So FEMAP comes with great default settings for all the analysis types. With more complex load and boundary conditions, multiple subcases are usually required, which can be laborious to create and set up. FEMAP can easily create multiple analysis sets that specify the solver and also the analysis type, and you can actually store those within the model. So there's no setup data that is lost there. The user interface here provides a visual display in this tree-type structure, which is organized into a very logical structure. It has subsets, as you can see. This gives you easy access to all these solver options. Also, analysis sets can be stored in a library, allowing easy access for repeated use and basically giving availability for all these analysis sets to other engineers. Many tasks that have to be performed to create a finite element model or even reviewing the results can be very repetitive. FEMAP offers a powerful way of automating these repetitive tasks and even customizing workflows through the API interface. Interaction with other third-party programs is also possible, so you can actually exchange data between them. FEMAP's API capability is an object-oriented interface that has direct access to the complete back-end of the FEMAP database. It is OLE COM compliant and can interface to other third-party programs like I mentioned, such as Word and Excel, for example. It's a fully featured VBA programming environment inside the FEMAP interface, and it includes features such as an IntelliSense function descriptor to help with function selection, also a step-through interactive debugging capability. You can, of course, optionally work in an external environment, such as Visual Studio if you prefer. By the way, FEMAP is delivered with a vast library of pre-written API programs that can be accessed right off the toolbar in the user interface. Let's talk about some of the challenges that faced Solar Impulse in their quest to fly around the world using only solar-powered structures. So that included the need to optimize all of the structures and components on the plane to minimize weight, of course. Keys to success here included the use of an integrated FEA solver and pre- and post-processor, which extended to perform advanced analysis types as well. They also had to import CATIA geometry, and that was very important, as well as the ability to create custom functions using the API I just talked about. Fast interpretation of the results using FEMAP's data table and the ability to combine load sets are also key benefits. As a result, the aircraft redesign allowed for a 3 times reduction in cockpit size between the prototype and SI-2 aircraft, for only a 2 times increase in weight. And the weight of the wing was kept to a minimum due to the ability to optimize the carbon fiber ply thickness inside of FEMAP.
Thanks, Dan. So to wrap up, FEMAP has a lot of powerful modeling and visualization functionality, all accessible within an easy-to-use and intuitive user interface, which brings many benefits, including increased productivity, a reduced learning curve, and training overhead. In the pre-processing stage, FEMAP offers the ability to import geometry from just about any source and has the functionality to efficiently convert that CAD geometry into a simulation model. A key part of that is the meshing process, which is made easier with FEMAP's high-performance meshing tools. In the post-processing stage, FEMAP offers a wealth of results viewing functionality to help engineers interpret the simulation results and better understand the model behavior. Essentially, FEMAP sets new standards in open simulation by being both CAD independent and solver neutral. In that, FEMAP can create simulation models for all the major commercial solvers, and FEMAP is fully integrated with Nastran. One last point about open simulation concerns FEMAP's application programming interface. The API allows FEMAP to become a powerful integration program for third-party solutions and significantly increases the portability of data into and out of the program. So for further information about FEMAP and to get hold of the actual software for a limited trial at no cost, as well as the information on mentoring, training options, or anything else related to FEMAP, just give Ceratec a phone call, send us an email, or visit our website. And we have a team of sales and application engineers that would be happy to be at your service. So with that, I'll hand it back over to you, Andy.
Great, thank you, Jeff. Now, obviously, there's a lot of information that we're trying to, present to you. So this is only the tip of the iceberg. If you have any questions at all and you want to ask, now's the time. Just go ahead and enter them into the chat panel, and Dan and Jeff will address them. Or if you're a little shy, feel free to pick up the phone, call us, or shoot us an email, and one of our excellent solution consultant or application engineer can get back and talk to you offline. Also, Jeff or Dan, what is the one or two takeaways that you want our attendees today to take with them as they leave this webcast?
Sure, Andy. So I can take a stab first. Sorry, Jeff. So for me, real quick, I would say the main takeaway, if you are considering FEMAP or any other pre and post processor, is the fact that it's so open in every way. So you can import any type of CAD geometry from any package and work with it very easily, as well as it's solver neutral. So even if you had some very advanced solvers such as LS-DYNA for an impact, for example, you can use any solver you want with FEMAP, which is an amazing pre and post processor. Sorry, go ahead, Jeff.
No, Dan, that's took the words right out of my mouth. That's I echo that exactly. Just the open API, the fact it's CAD and solver neutral, are just make it a very widely used and along with the easy interface. I have a lot of our customers tell us they just, if they don't have any pre-experience using an FEA tool, just using FEMAP out of the gate, with some initial training, they're up and running pretty quickly. So it's also very easy to use in addition to having the open API and being CAD and solver neutral.
Great. Thank you, gentlemen. Well, I see that we're 3 minutes over our allotted 45. So at this time, I'd like to thank everyone for joining us today. And don't forget to follow us on social media. We're on all the channels, and this webinar will be on our YouTube channel. So just go on YouTube and search for Ceratec Inc. And if you need to rewatch this or share this with a colleague, that's a place to go. Thanks, everyone, and have a great day.